Okay, section 2.4 is rates of change and tangent lines. So finding the average rate of change. Finding the average rate of change over the interval of this function over the interval 1 to 3. So first, let's just draw a quick little sketch of this function. It's a cubic function. If I find the zeros of this function, I'm just going to do this off to the side. To find zeros, I'm going to do some factoring. So that's x, x minus 1, x plus 1. That gives me zeros at -1, 0, and 1. And I want to go over the interval from 1 to 3. So this is the interval I'm using. This function looks something like this. And then it goes up at a curve. So from 1 to 3, if I find the average rate of change, that's going to be the slope of the line, and it's almost on the curve. I'm going to exaggerate that portion a little bit, the portion of the curve from 1 to 3, and make it a little bit more curvy than it really is, but just so that we can see that the tangent line is going to be inside of that curve, that slight curve that we have going up. So a slope is simply, or the rate of change is the slope of the secant line. So another way to say average rate of change is the slope of the secant line, which is the slope from 1 to 3. So when I plug in f of 3 minus f of 1 over 3 minus 1, that's just my slope equation, y minus y over x minus x. F of 3, if I plug in 3 to my equation, that's 3 cubed minus 3. Plug in 1 to my equation, 1 cubed minus 1. And I will get 27, that's going to be 24 minus 0, 24 over 2, which is 12. So my average rate of change is a slope of 12. It's pretty steep. And that's, again, the slope of the secant line. Now what we're going to look at next is what happens if I want to find the instantaneous rate of change at a point. So if I have a curve and I want to find the instantaneous rate of change at this point A. If I find another point, that's going to give me an average slope. But if I bring this point here closer and closer to A, move it towards the left along the curve, as I get really close to A, you can see that they're so close together that I am finding the slope at a given point. So let's see how that works. So again, the average rate of change is the slope of a secant line, the slope between 2 points. The instantaneous rate of change is the slope of a tangent line. So this is 2 points on the curve. A tangent line crosses at 1 point on the curve. Instantaneous, at a moment in time. We define the rate at which the value of the function y equals f of x is changing with respect to x. In other words, that's talking about delta y over delta x, the value of the function changing with respect to x at any particular value, x equals a, to be the slope of the tangent to the curve y equals f of x at that point that we have picked. So again, this is the definition of instantaneous rate of change, or slope of a tangent line. Okay, here's another explanation, a little bit more graphic. The slope of the secant line, shown here in red, is f of x plus h, that's my y value of my second point, minus f of x, the y value of the first point, over x plus h, the x value, minus the x. You can see that this denominator simplifies to h, so we have f of x plus h minus f of x over h. This is the slope of the secant line between 2 points where h is some distance between the two values that we are calculating. This is a simple, good old slope. This is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. When we limit h to 0, in other words, when I make h smaller and smaller, if I bring this point in until there is no difference between the 2 points, if h is 0, x plus h comma of f of x plus h becomes x f of x. The 2 points of contact become a single point and the secant becomes a tangent. So the slope of the tangent can be found using this same formula, but finding the limit as h approaches 0. The limit is what allows us to find the slope at a single point. So let's try one. Find the slope of the parabola y equals x squared at the point 2, 4. So at this point, I want to find the slope of the tangent line. Okay? One way to do it is to sketch a tangent line and get an approximation. So it looks to me when I draw this tangent line that it might, cross somewhere here, and I could count a slope, but that's a pretty rough estimate. So let's look at our definition. We want the slope of the tangent line. We'll actually want an equation for the tangent line. To write an equation of a line, I need a slope and a point. So we are given the point. We've got that. Let's find the slope. So the slope is the limit as h approaches 0 of f of x plus h minus f of x over h. You need to know this formula. Don't forget to write the limit in the front, because without that limit of bringing h closer and closer, all we have is the slope of a secant line. So the limit makes it the slope of the tangent. So for this function, we're going to use 2 for my x value. So I want the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. Limit as h approaches 0. You notice I'm writing that every single time. That is so critical. Do not leave it out. So plugging 2 plus h into my formula, that's going to be 2 plus h squared, minus plugging 2 into my equation over h. Let's work this out. So foiling this, I get 4 plus 4h plus h squared minus 4 over h. My 4's cancel, and I can divide everything by one of my h's. In other words, I can factor an h out of the numerator. These cancel. Now, up to this point, if I had plugged in 0 to get my limit, I would always get 0 over 0. As soon as I cancel and simplify this, I can now plug in my 0, and now my answer is 4. I don't need to write the limit anymore because I've plugged in the 0. I have found the limit when 4 plus h approaches 0, and my answer is 4. So that is my slope. My slope of my tangent line, I like to use a sub t to know it's a tangent line, is 4. So now back to my problem to write my equation. Y minus this 4, y minus y sub 1 equals my slope times x minus x. I can leave it in this form, or if I want to do some distributing, and then bring the 4 to the other side. So there's my equation. So negative 4 with a slope of up 1 to the right 4, up 1 to the right 4, up 4 to the right 1, and it looks like that is my tangent line. Okay, so I've done two things. I've written the equation of the tangent line, and I found that the instantaneous rate of change of the function f of x at x equals 2 is 4. I am increasing at a rate of 4 units on the y-axis for every 1 unit on the x. All right, let's take a look at another one. Oh, I'm sorry, let's do a little bit more definitions. The difference quotient then is the difference between two separate points. Remember that difference quotient, is the slope of a secant line or the average rate of change. Now, the slope of a curve at a point is of the curve at the point a comma f of a is the number m, and this time we've added that limit notation. So this is the slope of a tangent line or the slope of a curve at a point, and this is the instantaneous rate of change. The difference between average rate of change and instantaneous rate of change is taking the slope between 2 points versus taking the slope between 2 points that are coming closer and closer using a limit equal to 0. So really important to know these two formulas and to know what they mean and how they relate to rate of change. Okay, so here's another problem. We're going to do 2 more examples. F of x is 1 over x. Find an equation for the slope of the curve at any point x. Where does the slope equal negative 1/4? And describe the slope of the curve at any point. Again, if I can without too much trouble, I like to draw a sketch because it makes it easier for me to look at things. Okay, so there's my sketch. Find an equation. Now it doesn't say find the slope of the curve at a point. It says find an equation for the slope. So I don't know what x value I'm going to use at this point. So I'm going to change my equation just a little bit. Instead of saying a plus h, where I know some x value, I'm just going to keep it as x. And I'm going to keep the x in there, but plug it into my equation like I did before. So the limit as h approaches 0, f of x plus h is 1 over x plus h, minus f of x is 1 over x, all over h. I need to simplify this. Again, if I plug in 0 right now, I would get 1 over x minus 1 over x, which is 0 over 0. I can't do that in math. So let's simplify the numerator if we can. In order to add those together, I need a common denominator. So I'm going to multiply the left by x over x, the right by x plus h times x plus h, creating a common denominator. So x over x times x plus h minus x plus h over x times x plus h, all over h still. Combining my numerators, I've got x minus h. Remember, this minus sign needs to be distributed. All over x times x plus h over h. These will cancel. And if I multiply by the numerator by the reciprocal of my denominator, I have negative h over x times x plus h times 1 over h. Notice all of these steps, if I tried to plug in my 0, I would still have 0 over 0. Here's what happens though. Now I can cancel. Now I can take the limit as h approaches 0 of negative 1 over x times x plus h. Now if I plug in my 0, I get negative 1 over x squared. This now is a formula for the slope of this curve at any point. No matter what point I want to find the slope at, if I plug it in to negative 1 over x squared, which is going to equal my slope of the tangent at any point, I can get a slope. So this question, so that's all part A. That's my answer to part A. B, where does this slope equal negative 1/4? Well, let me set them equal to each other. So I hope we can see here that negative x squared has to equal negative 4. X squared equals 4, so x is at plus or minus 2. So at plus 2, if I draw a tangent line, my slope here is going to be negative 1/4. And at negative 2, whoops, if at -2 I draw a tangent line, its slope will also be -1/4. Those 2 points have the same slope. Part C, there's many ways to describe the slope of the curve at any point. First of all, I notice that the slopes are all negative for this function. No matter where I draw a tangent line, my slopes will be negative. I also notice that as I go out towards infinity, my slope will approach 0. And as I come in towards 0, my slope either becomes a super big negative value. So we'll talk more about drawing sketches of tangent lines and being able to find slopes from those. All right, one more. A normal line. A normal line is a line that is perpendicular to a tangent line. So let's find an equation of the tangent line first. So to find the tangent, I need a slope, in this case at x equals 1, and I need a point at x equals 1. So I'm going to say that the point is 1, 3, just plugging 1 into my function. So let's find our slope using this point and using my definition, limit as h approaches 0 of f of, since I want it at 1, I can put in my 1 plus h minus f of 1 over h. If you want, it might be a nice idea to pause the video, see if you can come through and get your slope on your own. I will keep working. So 4 minus 1 plus h squared minus, I'm going to put a parenthesis so I don't forget that negative sign, 4 minus 1 squared over h, the limit as h approaches 0 of 4 minus this whole thing squared, 1 plus 2h plus h squared minus 3 over h, the limit as h approaches 0 of 4 minus 1 minus 2h minus h squared minus 3 over h. 4 minus 1 is 3. It cancels there. I can cancel my h's. So I get, factor out an h at the top. Cancel those. Now I can plug in my 0 and I get -2. So the slope of my tangent line at x equals 1 is -2. If the normal line is perpendicular, the slope of my normal line is positive 1/2. The point is still 1, 3. So y minus 3 equals 1/2 x minus 1. And that is the equation of my normal line. Okay, so we did quite a few examples. I hope that will be helpful, and we will do some more work on this in class.